In today's video, we are going to be taking a look at ionic bonding, going over some of our basics of ionic bonding, and also talking about lattice energy. So to begin with, ionic bonding is when we have electrons being transferred from a metal to a nonmetal, forming ions. So in ionic bonding, we end up with positive and negative ions, and that is what holds the crystal together, is that attraction between our positive and our negative ions. Now, it's important to remember that if we have an ionic compound like NaCl, it is not just one sodium ion and one chloride ion. Ionic compounds form large 3D crystal structures of a repeating pattern of ions. So something like sodium chloride, we have a 1-to-1 ratio of the sodium ion to the chloride ion. If we had something like magnesium fluoride, that would be in a 1-to-2 ratio. So the formula gives us the ratio of the ions in the big 3D crystal structure. Lattice energy is the energy required to completely separate 1 mole of an ionic compound into its ions in the gas phase. So if we have something like NaCl, if I've got 1 mole of NaCl, if I want to completely separate that into the sodium ion and the chloride ion, that will take 788 kilojoules per mole. So that's the amount of energy it's going to take to rip apart the sodium chloride into its ions. The lattice energy will always be endothermic because it's going to take energy to separate those positive and negative ions. So then if we reversed the reaction, the formation of the ionic compound would be exothermic. Now, lattice energy will give us a good idea of the attraction between the positive and the negative ion. If we have something that has a lattice energy of 1,500 kilojoules per mole, that would tell us that those ions are more strongly attracted to each other than sodium chloride. And that would be based upon Coulomb forces. So we would be taking a look at the charges of the ions and the distance between the two ions. So we are just going to take a look at a few things in this chart. So if we compare lithium chloride to sodium chloride, they both have +1 cation, -1 anion. So their two charges are the same. However, lithium is going to be a smaller radius than the sodium ion will be. So lithium can get in closer to the chloride ion, so there is less distance between ions. So that's why lithium chloride is going to have a greater lattice energy than sodium chloride because it's going to have a stronger attraction between the two ions, since lithium ion would have a smaller radius, shorter distance, greater attraction. All right, now if we took a look at sodium chloride versus the magnesium chloride. So we notice that magnesium chloride has a way greater lattice energy than sodium chloride does. And that is because magnesium ion has a +2 charge. So with that greater charge, there will be a greater attraction between the positive and the negative ions. Therefore, it's going to require a lot more energy to separate the ions. Now that's going to be even more pronounced once we get down here, because the magnesium ion would be +2 and oxygen would be -2. So again, with those increase in charges, that is like stronger magnets. They're going to be more attracted to each other. Those Coulomb forces are going to be stronger. The ions are going to be more attracted to each other. Hence, the lattice energy, the energy to separate the ions, will increase. So as a reminder, that is our formula for Coulomb forces. And again, you will cover that in physics. We don't have to do any calculations with that, but we do need to know that our attractions, our force of attraction, will be dependent on charge. So as we could see on the previous slide, if the ions had a greater charge, there would be a greater attraction. Hence, the lattice energy would increase. So lattice energy will increase as the charge on the ions increases. So again, if you have a +2 and -2 ion, they're going to have a greater attraction, greater lattice energy than a +1 and a -1 ion. Our other factor that we have to look at is going to be the distance between the two ions. So as the distance between our ions decreases, if our ions can get in closer together, there will be a stronger attraction, so the lattice energy will increase. This again is Coulomb forces. So when we have greater charges, greater attractions, if you have things that can get in closer, so less distance, so smaller radius, that's going to also equal stronger attractions. So the lattice energy, the energy to separate the ions, will increase. All right, so we have an example to look at. We need to arrange the 3 ionic compounds here in order of increasing lattice energy. So we have NAF, CSI, and CaO. So we want to go from lower to higher lattice energy, or greater. So our most important factor to look at is charge. So Na is +1, fluoride is -1, and CSI, that's +1 and -1, and in CaO, Ca would be +2, O would be -2. So that is going to be our winner. So CaO is going to have a stronger attraction because they have greater charges. So therefore it has greater lattice energy, meaning more energy to separate the ions. All right, the tiebreaker between our two that are both +1 and -1 is going to be atomic radius. Sodium and fluoride are going to be smaller ions than cesium and iodide. So since these two are going to be smaller, they are going to be able to get in closer to each other. So less distance between the ions equals a greater attraction between the two ions. So greater Coulomb forces, greater lattice energy. CSI is going to have our lowest lattice energy, meaning it's going to be the easiest to separate because lower charges, +1 and -1, and larger ions. So therefore, they can't get in as close to each other. They'll have a weaker attraction. In this example, we are looking for which one would have our greatest lattice energy. So we have 3 compounds. First thing we have to look at is charge. So with magnesium fluoride, magnesium is going to be +2. Each fluoride ion would be -1. Calcium fluoride would be the exact same thing. Calcium is going to be +2. Fluoride is going to be -1. And in ZrO2, Oxygen is going to be -2. So therefore, ZR would be +4. So that is going to be our one with the greatest lattice energy because those ions have the greatest charges. So therefore, they will be the most strongly attracted to each other. Real quick, we need to mention that our transition metals, groups 3 through 12, the octet rule doesn't apply. As we talked about when we were doing electron configurations, our transition metals tend to lose the s electrons first, and then they may also lose some d electrons too. So the octet rule does not apply to the transition metals and polyatomics. So if we have our polyatomic ions, things like nitrate or sulfate, hydronium, hydroxide, we will be drawing those differently. We'll be looking at those in the next couple of days. Within the polyatomic ion, so in nitrate, the N and the O's are joined by covalent bonds. Together, they carry an overall charge, and then the polyatomic ion will be attracted to an oppositely charged ion to make the ionic compound. So they also won't always follow the octet rule, and we'll draw those in a few days. All right, lastly, just real quick, some properties of ionic compounds. So if we think of table salt, NaCl, that can help us with our properties. So they're crystalline solids, which means that they are large 3D crystals of repeating ions. They have very high melting and boiling points. Our ionic salts are not going to conduct as a solid, but will conduct as a pure liquid. That's what molten means, pure liquid, and as aqueous solutions. So remember, you need free-moving charged particles in order to conduct electricity. In the solid phase, our ionic salts, we have our charged particles. They are not free to move, therefore they cannot conduct electricity. Once they are melted or aqueous solution, then the ions are free to move, can carry the current, and they will be excellent conductors. And then for our ionic compounds, largely soluble in water. We did our solubility rules earlier in the year, like group 1 is always soluble, nitrates are always soluble, acetates are always soluble. So a lot of our ionic compounds are soluble, but we do have to refer to our solubility rules to get more specific.